Hello friends, today's question. A man grows into a giant such that his linear dimensions are increased by a factor 9. Assuming that his density remains same, the stress in the leg will change by the factor of. So in this case, we have to find out the stress which is in the leg of this giant person changes by the factor if it grows from the normal to a giant person. Okay. So basically, in this case, we are going to find out how the stress, that is force as well as area, is going to change if its only linear dimensions are changing. Okay. So we start from the basic thing which states that stress represented as sigma is our force oblique area, where F is the force and A is the area of cross section. And force, which is nothing but our weight, will be equal to volume multiplied by density. So you can say the force, which is our weight, will be directly proportional to V multiplied by rho, where this V is the volume of the man, and rho is the density. And let's find out how the volume and the area of cross section both vary as the linear dimensions are going to change. So we say that volume and area scaling. Volume and area scaling. So we know that volume is directly proportional to the cubic of the length. So it means it scales by the cube of the linear dimension. You can say that volume scales as a cube of linear dimension. And if linear dimension is represented as L, so we can write formula that our volume is directly proportional to L cube. Similarly, we can write that our area scales as a square of the linear dimension. Area means cross-sectional area. Area scales as a square of linear dimension. Therefore, A is directly proportional to L square. Now it is given that the scaling factor of the linear dimension is 9. So we are given the scaling factor of linear dimension is 9. So if L prime is our new linear dimension, then this L prime will be equal to 9 times the original linear dimension, that is equal to L. So we are going to use this relationship to find out new volume with the scale linear dimension. Therefore, we can say the scaled volume if represented as V prime will be, you can say it comes as directly proportional to L prime cube, and L prime we already know is equal to 9 times L. So we can write this as 9 times L and whole cube. So we get this as V prime will be equal to, we have this as 7 to 9 L cube, and our L cube is our original volume. So we can say scaled volume V prime V is equal to 7 to 9 multiplied by original volume V. Similarly, we can write the scaled area. If we represent it as A prime will be equal to L prime square, and L prime is our 9 times L whole square. So we get this as that A prime will be equal to 81 times L square, and L square is our original area A. So we get here A prime, that is scaled area, will be equal to 81 times original area. Now we find out the scaled stress. And yeah, so next is our scaled stress. Let us call this as sigma prime will be equal to F prime oblique A prime, and our F prime is our, you can say, directly proportional to the scaled volume, and scaled volume we found out that our F prime will be equal to 7 to 9 multiplied by V, and V is directly proportional to S. So this gives us that F prime will be equal to 7 to 9 times F. We substitute the value, we get this as that sigma prime scaled will be equal to 7 to 9 F, and A prime is equal to our 81 times A. So we can write this as 81 times A, and this F upon A is our original stress. So we can write this will be equal to 7 to 9 will be coming as our 9 F upon A, and this equal to 9 times sigma, that's the original stress. Okay. So we were supposed to find out the stress in the leg changes by the factor of 9. So the option number D is the correct option. So from here we can write that the stress changes by the factor of 9. Factor of 9. So the correct option was our D option. You can say correct option is D. So this completes the question. Thank you.